A beginning of statistics. We'll see how far we get today. We may have to carry this over into Wednesday too. So what we're going to start learning how to do is run what's called an average. Now I think we know, we've heard the word average before. When you hear the word average, what do you think of?
The sum of the number divided by the total of the number.
Sum of the data divided by how many data? That's the old formula, yeah?
Yeah.
So add all the data up and divide by how many there are. Love that. Love that. Okay. Why do you do that? Why do you do that?
To get the average.
But why? Why that formula?
We're never told why, remember?
You never. Oh shit! That's right.
Just do it that way.
You just do it, yeah.
Hang on. Hang on. Hang on. Hang on.
Oh.
Oh man, I wish I could. Okay. Give me 5 people up here. Give me 5 people. Just any 5 people will do. Thank you. I think I can make this work. I would have brought more props had I expected that. I forgot that response. Closed all the way. We got 5. Beautiful. All right, Tony. There you go. Aaron, there you go. Go, Galena, and Chelsea, don't get in. Stand in a row if you would. If you're so kind, my friend. Stand in a row. If you'd be so kind. This is a little sub-lesson. Okay. I've given them all a deck of cards, or some decks of cards, depending on who they are. They got different numbers. On average, how many decks of cards do they have? And you're not allowed to use the formula that Kelly just quoted. You're not allowed to use the formula that Kelly just quoted. You're not allowed to use the yes you do, Shelby. Good. I was nervous about. I was hoping that maybe that had trickled down by now, but maybe not.
So they can pass the cards down until everyone has an equal amount.
Aha! So, did you hear what Shelby just said? Shelby's idea is, in order to figure out the average number of decks of cards these students have, we should redistribute the cards so that each of the folks up there
Has an equal amount of cards.
has an equal amount. Let's do that. Hopefully I counted right. This should work out evenly if I counted right. I did it very quickly. So poor Chelsea's got nothing. Give her some cards.
So how many decks?
Tony, quit Bogart. Don't ask her how many decks because you don't know. I don't want you to count how many decks there are.
Okay.
Distribute until you all have equal amounts. If I did it right. Tony, quit Bogarting.
Chill out over there. Alright, I got 4 now. You got 3.
I think you have 5 now, Tony. I think you have,
Yeah. Okay, so I can't count. Alright.
Well, I can't count either, but I can just see.
1 each there. Now we all have 3.
Aha!
So it's 3.
So the average number of decks of cards per person in the beginning, when Tony had 6, I think, had a whole
7.
bunch. 7. Chelsea had none, and you guys all had different amounts. Aaron, you had 1. But on average, you guys have 3, because once you redistribute the resources equally to all the data points, the result is 3. Do you see how that's what the formula does, friends? I know, I was worried that was going to happen, Tony. My apologies. Just don't have to worry. I'll deal with it later.
That's all good.
Do you see how that's what the formula does? When it says sum up the data and then divide by how many data points, what you guys would have done was you would have added all your decks of cards together to get 15, and then divided by 5, and it gets 3. So what you just did was you did it without using the formula. So the idea of an average is it gives every data point an equal share. If we ran the experiment this many times, it would take this many if we equaled out the results. Fair enough? That's what an average is. Thank you. You guys have been a wonderful audience. I appreciate that. Thank you for your participation. And Aaron, it breaks my heart whenever I hear we don't know why something is the way it is.
Well, it just seems like that's what's always happened.
I know.
I just want to say my wealth just got redistributed.
Ah! Now did you hear what Tony just said? My wealth just got redistributed, which is oftentimes one of the criticisms of using the average in certain concepts is, I said, Tony, quit Bogart. One of his responses could be, you know what, I earned this, screw you. I'm not going to redistribute this. That's one of the arguments about using the average. And the averages can be misused. And I'm not saying they always are used correctly. But that's what an average actually is. An average actually does just that. It takes the wealth or the resources and redistributes it. Fair enough?
I was just making a political argument
I know
as a
you were.
joke. But
I know you were. It's not, but it can be not funny depending on who you're talking to.
Well, I mean, if we were talking about money, forget you. But
Exactly. So yeah, but we're talking about coin flips, which isn't that big of a deal. So let's crunch an average on one of our data sets. Just one of them for now. Let's do the far right one first, which is the experiment of flipping a coin until we get a repeat. What I'd like to know, and I hate to do this, but I'm going to need some more board. I'm going to erase part of our beautiful collection here. Although you can kind of see how it lives. I mean, there's a flip till a repeat, right? There's a flip till a repeat. There's a flip till a repeat. So it's got some overlap with the data set we already have, but unfortunately I need more board and I'm out of window. So we're going to erase a little bit of our data set. It was gorgeous. I loved it, every bit of it.
we only have one window.
We do, but I think what I'm about to do is going to require more than that one little tiny window. So what I want to do now is I want to apply this idea of an equal share. I do want to tie this back into the idea of randomness too, per something Aaron said earlier, which is really, really cool. So, on average, what's the average number of flips until we see a repeat? Now we know, of course, there's only 4 possible outcomes. Heads, heads, tails, tails, heads, tails, heads, or tails, heads, tails. And those are the only 4 potential outcomes. Those are the only 4 potential outcomes. On average, though, how many flips does it take? Now, if there's 4 outcomes total, heads, heads, tails, tails, heads, tails, heads, tails, heads, tails. That's it. You can't have anything else. Anything else implies you missed the repeat. You went too far. What's a tempting average to use on average? So heads, heads, how many flips did that take? Tails, tails? Heads, tails, heads? Tails, heads, tails. So what's a tempting average to use? 2.5, isn't it? 2.5 flips, right? Because twice took, let's answer it this way. One way, either you have heads, heads, which is 2 flips. Tails, tails, which is 2 flips. Tails, heads, tails, which is 3 flips. Heads, tails, heads, which is also 3 flips. So one way of crunching this average, is to simply add those together and divide by the 4 possibilities. There's 4 data points, right? That one, that one, that one, or that one. So one way of looking at it is going, okay, well that's 2 plus 2 plus 3 plus 3 divided by 4. So number of flips up top, number of trials at the bottom, right? Number of data points at the bottom, and that ends up being 2.5, doesn't it? 2.5 flips on average. There's one answer. There's one answer. Do our data support that? Does our data look like it took on average 2.5 flips? What do you think? Look at our data. Look at our data and tell me if you think that lines up.
No.
Kelly's got a cautious no. Tom had a very deliberate no, it doesn't match up at all. Anybody say it does pretty much match up? Somebody saying, I'm not really sure how it matches up. I don't know if it matches up yet. I'm not real sure if it matches up yet. We better look at it more carefully. Now, it doesn't match up perfectly. Because what assumption did we make here? What assumption did we make when we did 2 plus 2 plus 3 plus 3? What assumption did we make about that when we added them all together? That didn't actually happen with our data.
Not consistent.
Boom! We didn't get the same number of 2s as 3s in our data. We got roughly 25% more, a little bit more than 25% more 2s than 3s. So, the assumption here is you're going to see the exact same number of 2s as you see 3s. And that's one way of looking at it, but that might not be correct. that might not be correct. What you should do is re-crunch the numbers with a nod to the frequencies that we actually saw. So let's crunch our data and see how that plays out. Now, this is the last thing we'll do today because we're out of time, and that's okay. We're going to extend this to our data for next time, which I'll save so we don't lose it. And then we're going to extend it to decks of cards as well. All right. So here's one way of doing it. But this way makes the assumption that getting heads, heads, or tails, tails is just the same as getting heads, tails, heads, or tails, heads, tails. It might not be. It might not be. It's just like saying if you calculate your GPA, if you got an A in your weightlifting class, and you got an A in Math 105, and you got a B in sociology, you just go 4 plus 3, divide by 3, and you're done. Well, you can't do that, because your sociology class and your weightlifting class are weighted differently. The HHP class is only worth 1 credit, whereas your social class and your math class is worth 4 credits. So you have to account for that, and that's the idea of using that distribution right there. So using our data, how many data points do we actually have? I just had to add it up in my head real quickly. How many trials did we actually run? Technically speaking, we have 189 of them, don't we?
Yeah.
Now, we should have had some multiple of 10, but of course I can't add. But looking at that, if you look at our data over here, there are only 2 distinct numbers, 2 and 3, but those occurred 189 times over the experiment. So in other words, I can redo my average like I did right here, but I've got to account for all those 2s and 3s. So I'd have to do something like this. This is going to get kind of annoying. 2 plus 2 plus ... plus 2 plus 3 plus 3 plus ... plus 3. Now, we got to make sure that whoever's reading this knows there are 108 of these, and there are 81 of these. And then I've got to divide that by 189, because that's how many we had total. You see how it's similar to this one?
189 divided by 189.
Careful. There's 108 twos. So it's 2 plus 2 plus 2 plus 2, 108 times.
Gotcha.
And it's 3 plus 3 plus 3, 81 times.
Oh, gotcha.
This is why we invent the multiplication. Nobody's going to do it this way, I hope. Oh my God, I hope not. What you're going to do is you're going to do 108 times 2, hopefully, plus 81 times 3 over 189. So Frankie, when you said 189 over 189, kind of,
I was just
but the 189 is split
Yeah.
because you have to weight the data. The data is still 2 and 3. Tom, when you said there are 2 data points, 2 and 3, you're technically correct, but you have to weight them with their frequency of occurrence. The 2s and 3s don't occur the same as they did over here. We saw more 2s than 3s, which leads me to believe that that's significant. We'll come back to why. All right, what does this average end up being, Aaron?
That's 2.5.
A little bit below? How much below?
2.4 rounded.
2.4 rounded. So here the average is 2.4. Aaron's comment is, well, it's 2.4, which is almost 2.5. Absolutely, absolutely. I'm not saying it has to be vastly different. I'm saying this is more accurate because it doesn't make any assumptions about how frequently things occur. It doesn't make any assumption about the frequency of heads, heads, tails, tails versus heads, tails, heads, tails, heads, tails. Does that make sense? We'll come back next time. I'll take a picture of this so we have it, and we'll crunch the data on flipping until heads, on flipping until you get one of each, and we'll see how they stack up, how the averages stack up. Cool? We'll play with cards next time too. All right. Thank you guys. Have a good rest of your day.
There's that in there.
I pulled it, closed it out before I could get to look at it. Ah, the whole point. Let it run for an hour.
Right, I was watching this, I could see the
Well,
shadow.
we'll run it again next time.
Yeah.
This is actually readable. I've got a sheet set up for you. So we have flips needed 108.